Hi, good morning. നമ്മൾ ഡിറേഞ്ച്മെന്റ്സിലെ ഒന്ന് രണ്ട് പ്രോബ്ലംസ് ചെയ്യുകയാണ്. അതിൽ ആദ്യത്തെ പ്രോബ്ലം പ്രൂവ് ദാറ്റ് dn is equal to n minus 1 dn minus 1 plus dn minus 2, where dn is the total number of derangements on the set A is equal to 1, 2, 3, etc. So let us start with the set capital A is equal to set 1, 2, 3, etc. n, and f be a derangement. F belongs to FF is a derangement on capital A. Now you consider the image of 1. Under F, 1 can have these as the images 2, 3, 4, etc. n. Because F is a derangement, F of 1 cannot be 1. So F of 1 can be any of these i's. So F of 1 can be any I from 2, 3, 4, etc. n. Now fix one such I, so that F of 1 is equal to I. Now we are going to count the number of derangements corresponding to this fixed I. Okay, then there are two possibilities. Possibility 1, f of I is equal to 1. F of 1, the image of 1 is I and the image of I is 1. So then this f will look like the image of 1 is I, 2, 3, 4, etc. I minus 1. I, image of I is 1, I plus 1, etc. n. Then we can see that under this f, this 2, 3, etc. I minus 1, I plus 1, etc. n has different images. Means none of them have self-image. So then in this f, we can find a derangement of the n minus 2 symbols 2, 3, etc. I minus 1, I plus 1, etc. n. So corresponding to every such derangement of these n minus 2 symbols, we can have an f of this type. So there is a 1-1-1-2 correspondence between the set of all derangements on n symbols in which image of 1 is I and image of I is 1 for a fixed I, and a derangement of the n minus 2 symbols 2, 3, etc. I minus 1, I plus 1, etc. n. And by bijection principle, there are dn minus 2 derangements on n minus 2 symbols. So there are dn minus 2 derangements of this type. Which type? The derangements on n symbols in which image of 1 is I and image of I is 1 for a fixed I. Okay. Now possibility 2, f of I not equal to 1. So it will look like the image of 1 is I, 2, 3, etc. I, etc. n. These will have different images. Then relabel this 1 as I. So simply call this 1 as I. Then here comes a 1, but that one is not the image of I. So it will come somewhere here as I. Is it clear? See in the lower row, the second row, I will not appear anywhere as image of 2, 3, etc. n, because I is already appeared as the image of 1. Now if we call this 1 as I, then 1 will come here in the second row as the image of something, some element other than I. Then if we call this as I, if we rename this 1 as I, then the remaining part, this part, is a derangement on the n minus 1 symbols 2, 3, etc. n. As in the first possibility, there is a 1-on-2 correspondence between the set of all permutations on set of all derangements on these n minus 1 symbols and set of all derangements on n symbols in which f of I not equal to 1 and one image of 1 is I. Again, by bijection principle, there are dn minus 1 such permutations. Since there are dn minus 1 such derangements on n minus 1 symbols, 2, 3, etc. Therefore, for a fixed I, by addition principle, for a fixed I, there are dn minus 1 plus dn minus 2 derangements on n symbols, satisfying this condition. And as I varies by multiplication principle, total number of derangements on n symbols dn is equal to, I can have n minus 1 values. So n minus 1 into dn minus 1 plus dn minus 2. This is the first problem. Now we go to the next problem. Prove that dn is equal to n dn minus 1 plus minus 1 the whole raised to n for all n greater than or equal to 2. See, we prove this by mathematical induction over n. We know that d1, the number of derangements on one symbol is 0, because if there is only one symbol, say 1, then 1 can go to 1 itself, so there is no derangement. So d1 equal to 0. And d2, the total number of derangements on two symbols is 1, and this being the only one derangement. And in fact, there are only two permutations on two symbols, 1 and 2. One is the identity permutation, 1 goes to 1, 2 goes to 2. And the other is this. And this is the only one derangement on two symbols. So d2 is equal to 1. Now d2 is equal to 1 can be written as 2 into d1 plus minus 1 the whole square. That is true. d1 is 0. So this is minus 1 square is 1. So the result is true for n equal to 2. So we assume that the result is true for all n less than, for all k minus 1. And we will prove the result is true for k. We assume that the result is true for n equal to k minus 1. And now we prove that the result is true for n equal to k. The result is true for k minus 1. Therefore, by induction hypothesis, we have dk minus 1 is equal to k minus 1 dk minus 2 plus minus 1 raised to k minus 1. dk minus 1 is equal to k minus 1 dk minus 2 plus minus 1 raised to k minus 1. And by previous result, we have dk is equal to k minus 1 into dk minus 1 plus dk minus 2. And from here, by induction hypothesis, what we have written now is k minus 1 dk minus 2 is equal to k minus 1 dk minus 2 is equal to dk minus 1 minus minus 1 raised to k minus 1. This is equal to dk minus 1 plus minus 1 raised to k. This minus is also accounted here. So dk minus 1 plus minus 1 raised to k. Therefore, see, this is from 1. Now from 2, dk is equal to k minus 1 dk minus 1 plus k minus 1 dk minus 2. And we have from 3, this is equal to k minus 1 dk minus 1 plus k minus 1 dk minus 2 is equal to dk minus 1 plus minus 1 raised to k from 3. K minus 1 dk minus 1 plus 1 dk minus 1. So this is k dk minus 1 plus minus 1 raised to k. Therefore, the result is true for n equal to k. Therefore, by mathematical induction, result follows. Next problem. Dn is even if and only if n is odd. So assume first that Dn is even. Assume first that Dn is even. And to show that n is odd, so we assume the contrary, that n is even. And by the previous result, we have Dn is equal to n into Dn minus 1 plus minus 1 the whole raised to n. And we assume that n is even. If n is even, this term is even. And this is 1. Since n is even, this is 1. And even plus 1 is odd. That shows that Dn is odd. That is a contradiction to the assumption that Dn is even. That is a contradiction. Therefore, our assumption n is even is wrong. Therefore, n is odd. And conversely, assume that n is odd. Conversely, let n is odd. And to show that Dn is even. Since n is odd, we know that n minus 1 is even. And if n, we showed that n, if n is even, then Dn is odd. So since n minus 1 is even, Dn minus 1 is odd. And again, use the above identity. Dn is equal to n Dn minus 1 plus minus 1 the whole raised to n. So what are the conditions? Dn minus 1 is odd. N is odd. So this product is odd. N is odd. So minus, this is minus 1. Odd minus 1 is even. Therefore, Dn is even. So these are the three problems for time being. And thank you.